Hi, I'm Russ. I want to talk about World Trade Center 7. There's a lot of conspiracy theories about that, but I wanted to give you a fire protection engineering and a mechanical engineering perspective on that collapse, how it occurred, and how it can be prevented. This source for the information here mainly came from the NIST, the National Institute of Standards and Technology. They performed a comprehensive analysis on this collapse, including advanced computer modeling. So some of the images you see came from that source, other ones from other applicable sources, such as the Society of Fire Protection Engineering Handbook, Fire Protection Engineering, AISC, American Institute of Structural Construction, or excuse me, AISC, American Institute of Construction. So a little few background details for WT7, World Trade Center 7. The collapse, obviously, September 11th, 2001. The construction completion for this structure happened in 1987. It was fully sprinklered. Ignition happened at 10:28 a.m. on September 11th, and the collapse happened at 5:20 p.m. No fatalities, and there was fire spread between floors. And what's interesting needs to be pointed out here is this was basically a 7-hour unrestrained burn. Buildings aren't designed to burn for that long. And that's what makes it very unique. This is different than other fires in high-rise structures. This is what led to the collapse. And there's very specific reasons for that that you'll see. So the location of WTC7 was just north of WTC1. And what's interesting about WTC7, to maximize area usage on Lower Manhattan, it was built over an electrical substation that served the area. So the first few floors were actually occupied by an electrical substation. They had to build a frame, a structure around that. That's part of the reason this particular building collapsed. Multiple fires were ignited from WTC1 collapse. No manual firefighting was available to deal with WTC7. And the reason for that is there were 343 firefighter fatalities with the WTC2 collapse and associated collapse of WTC1. And because of that, there simply was no available personnel to address the WTC fire. Even though the building WTC7 had an automatic suppression system, the infrastructure supplying water to that building was destroyed with the collapse, and consequently, there was no automatic suppression available for the fires in WT7. So really quick, let's go back and look at this initial picture. Take a look right here, kind of in the center of the picture. You can see that there was a fire that started kind of midway in this building due to the WTC1 collapse. Now, that particular fire seemed to have self-extinguished, and that's common. If you had a fire in an area that was constrained, that had limited combustibles, it would simply burn out. And the building itself was fairly robust. It had solid fire protected members, so it's reasonable that this burned out. But point is, regardless whether it continued to burn or not, um, the fact that you did have a fire here, you had fire at other locations, it clearly there was some fire transfer during the collapse of World Trade Center 1. The other thing that makes forensics challenging on this particular building was the light obscuration from the collapsed towers. Now, this is to the north. The WTC7 was to the north of the World Trade Center Complex 1 and 2 that were collapsed. And that dust kept on shrouding the north side throughout the day. And consequently, it was challenging to see where fires started and their progression because of that. There's telltale signs, as pointed out, that fires were there, but it was challenging because of the light obscuration to identify exactly how that fire occurred and where it transferred. So, some details on WTC7. It was a fairly unusual design. It was a trapezoidal type shape. It was different. This is an important point here. Column number 79. Column 79 is unique for several reasons. One, it's surrounded by very long members, and the second reason is this location, it's unrestrained. Now, normally in a building, take a look at like two beams here. You may have a couple beams at this location, but you're going to be restrained. So when you have thermal expansion pushing from one direction, you're going to be pushed from this other direction to keep the thermal expansion in check. And that is a normal, basically 90 degrees orthogonal type designs are typical for structural steel construction. This is different. This was very unique, and it has to do with two factors. One was the substation, but the other one was the truck drive-through for deliveries, things like that, that made this location unique. And if you look at the footprint, this is the standard footprint for upper stories. I think this was the American Express floor, but it just shows you that it had a very wide open office environment. So what you had, instead of a series of compartments, you had a cubicleville with wide areas. And if you look at the sub the subs I guess the structures over the substation, they had to build a series of structures to protect the substation. And column 79 here, what you can see is that it was a part of this substation protective structure. And if you look at it more closely, so column 79, these spans are 50 feet. So these are 50-foot I-beams here. And in some other videos that I did on my website, my YouTube channel for fire forensics, a couple different of those videos discussed thermal expansion as subset topics within metal deformation. But if you consider that typically you're going to have about on the order of about 1 times 10 to the minus fifth. So if you per degree Celsius. So if you have a 100,000 units length, and you raise something 1 degree Celsius, you're going to have a 1 out of 100,000 unit length change. So 10 to the minus fifth type relationship. So if you had 10 degrees, you'd have, 10 units. If you had 100 degrees, you'd have 100 units. If you had 1,000 degrees, you'd have 1,000 units, or a 1% type change. So here, if you had like 1,000-degree Celsius increase, which is typical in flashover conditions, you'd have a 1% change in your length. So if you're dealing with a 50-foot structure, well, that's 6 inches. You're actually expanding 6 inches at 1,000 degrees Celsius. So that expansion and then later the contraction results in moving your beams off of their, or your columns are supporting girders, and that expansion, what that does is it pushes girders off of columns or support mechanisms. So it's an important topic to consider when we look further into this. So what you had here is a penthouse over column 7. And it was very obvious from the demolition, well, not demolition, the destruction, the catastrophic collapse of that structure, that if you looked at where the penthouse was, it was over column 7 when the whole thing collapsed. That's where it started. And then after the forces were redistributed during that collapse, you saw basically like dominoes, the whole structure collapsed like an implosion. There's nothing necessarily nefarious here in terms of some of the conspiracy theories, and that's why this discussion is being put on YouTube, so you can understand the forensics as reported from NIST in terms of the actual computer modeling. We'll go through some of the conspiracy topics, a few of them, just to explain things. So if you look at the actual fire modeling, so your column 7 is going to be in that vicinity. And what happens is over time, you may not have flashover in those wide areas, but what you do have is what's called a traveling fire. So you have a fire start, and then it moves and expands and broadens, and then you have significant heat applied in the column 7 area over time. And that's the key element, time. because these structures, this particular structure had an excellent fire rating. I believe it was 2 hours, this location, but because it burned for 7 hours, you had heat transfer going into those beams in fairly, fairly hot environment. And what that did is it weakened the material to a point where it really couldn't resist the applied loads. So if you take a look at the actual, this is a structural um, analysis as a function of temperature. And you look at this column 7 location over time, you can see that it gets hotter and hotter and hotter by the time 5 p.m. rolls around. So you have 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m. By the time you're at 5 p.m., I mean, you're hot. You're, 500 degrees Celsius. It's a very hot environment by column 7. So if you look at that and understand that about 550 degrees is typically used, degrees Celsius, is typically used in structural design for having no load. And I'll show you some charts that indicate it's about 538 degrees Celsius is when you have about 50% of your structural steel. And that's really the target for structural analysis. And let me just back up a little bit. Typically, when you're doing a structural load, it depends on who you talk to, but for the most part, the margins are pretty tight. If you look at the chapter, I think it's chapter 16 in the International Building Code that targets structural design, there's about a 25% safety factor built into that, which is typically assumed. Other sources might suggest, particularly in this earlier design, 1968 New York City Building Code, more of a 10% design. So you had basically a 10% margin. So you're always going to overbuild structures. And then there's another factor called redundancy. So when you have a structure, um, if you have one, your design, basically what you do is when you design a building, you're designing a fire to happen in a particular location and a particular set of circumstances. You have multiple passive and active features to fight that fire, and then you're always going to rely on manual firefighting. So you're not going to design a building for widespread fire travel. And because of that, you can design a system for a structure that if you collapse, weaken a certain area to collapse, you're going to have redundant members in your design that are going to take up the slack for that localized collapse. So it's a principle called redundancy. And there are some series of analyses done, carding tests, for example, that demonstrate that you have redundant transfer of loads so that you're not going to collapse the facility. But what was interesting in WTC7 is it wasn't a concentrated fire. It wasn't the loss of just column 79 in this case. It was multiple columns that lost their strength because of prolonged exposure to high elevations of temperature. And that resulted in multiple columns failing, as this image shows. So what you had is at column 79, it may have initially buckled or failed through probably buckling. And there's some other features that hopefully I'll get the chance to address here. But what you had is once that happened, there was other portions of the structure that were also weakened by that thermal heat transfer and thermal expansion and resulting loss in yield strength. So you may have had what appeared to be like an implosion under the penthouse, under column 79, but because of the other weakened members, you had a series of dominoes. So the redundancy was lost, so the force transfer to redundant members, other columns through the girders and beams, what happened is those didn't have the resistive strength left within them. So once column 79 failed, you saw a series of dominoes that took down the entire facility because of the weakened state. The temperature had been raised up in too many locations and weakened. And I'll show you some other stuff here. So thermal expansion occurring at temperatures hundreds of degrees below typical for design. So that's an important feature. And it has to do with the redundancy, and it has to do with a traveling fire. So if you're designing a localized failure, you're going to do so for a flashover situation. And it is, typically flashover is going to have about 1,000 degrees Celsius, but you're going to have spikes up to about 1,300 degrees Celsius. And then it's going to hover around 1,000 degrees Celsius. for flashover conditions. And let's define flashover conditions. Flashover is when you have just a crazy sudden rise in temperature and heat flux within something due to the compounded thermal transfer due to reflection from your walls and your ceiling. So if you have a fire, normally that radiative heat transfer can take that energy out of out of an area, but in a compartment, in a room, the wall is going to reflect some of that energy back. And you hit this critical point where the energy just exponentially goes really high. And then suddenly you don't have enough oxygen to sustain combustion. It goes to what's called a ventilation limited fire. And at that point, those hot gases are ready to combust. They're hot enough to combust. They have ample fuel to combust, but what they don't have is oxygen. And they're going to travel throughout until they find the oxygen. So typically when you see broken windows and flame emerging from a window or a door, that is a ventilation limited fire. You're in full flashover at that point. So there were certainly places within WTC7 that had flashover, but much of the fire had to do with traveling fires, where you, because of the wide open footprint, you weren't dealing with compartments, you were dealing with an office space that had 50-foot spans. So because of that, what you had was a traveling fire that would burn up its combustibles but not reach enough heat flux to initiate flashover. So you may have been, 600 degrees Celsius, but you never hit that 1,000 degrees Celsius that's typical for a flashover situation. It's not to say some areas didn't. Some areas clearly did reach flashover. But generally speaking, you had widespread damage within that facility and prolonged exposure to temperatures that were hundreds of degrees Celsius below flashover conditions, yet had high enough and elevated enough temperatures to weaken steel and also deform metal enough to move beams and girders away from their supports. So that's the principle here. It was typically you're going to design for flashover, but WTC, it was a combination of flashover and prolonged exposure to elevated temperatures. So you had thermally induced lateral lows, and the structural failed to include preventative design for fire-induced progressive collapse. And that had more to do with the redundancy principle, the principle of redundancy in design. The beams were just too hot. So at the time, NIST did determine that design was consistent with the New York City Building Code that was applicable for this particular design. The sprayed applied fire-resistant material was also compliant with the New York City Building Code. This is a topic that I'll address further, and it's worth considering, was that adequate? And are buildings today meeting adequacy from a fire protection engineering? Because the American Institute of Steel Construction may have some different interpretations. So this is basically the threshold for design. It's 538 degrees Celsius for steel. If you look at why that is, it's based upon, this is from the SFPE Handbook of Fire Protection Engineering. But what happens over time with steel, is there's two factors. There's the yield strength, the actual strength of the steel, and then there's the elasticity of steel. So it's like a spring. If you have a spring, a certain amount of force, you exceed that force, it's going to be deformed. So the modulus of elasticity gives you the amount of stress you can apply to that spring and still have it come back to its original form. Now, you may think non-intuitively, but a beam can also be modeled as a spring using what's called Hooke's law. If you apply a load or push it or pull it, it's going to spring back. And what happens at elevated temperature, not only does it lose that springiness, the force that it pushes back, but it loses this overall yield strength. And typically, annealed steel is about 35,000 psi, pounds per square inch, for its resistive yield strength. And if there's different alloying concentrations and work hardening and things like that, that you can get the steel up substantially more than that. But typical structural steel, for the most part, I think is about 35,000 psi. So this is an interesting, what's called ASTM E119 test. And E119, the E119 standard fire, it's a furnace that's it has a specific size to it, and I think it was developed about 1918 thereabouts. And what it does, 1908, 1918, something like that. But what it does is it has a very specific temperature profile that you test materials in for. So if you have a fire rated door, like a 1 hour fire rated door, what it does is in the ASTM E119 test furnace, it has to maintain certain structural integrity, and the energy passed through that door can't exceed certain metrics. And there's certain, valuations, 1 hour, 2 hour, 3 hour, 4 hour. So this particular chart, what this shows is a beam, a standard structural beam in fire conditions in the ASTM E119 standard fire furnace. So anytime you hear standard fire, the standard fire is the ASTM E119 model. So this particular I-beam, what's interesting here is you have concrete on top, and that would model typical application for structural steel. What you're going to do is have a beam and then have concrete on top. And what's important to note about that is in a fire condition, that concrete above a beam, that flange, it's going to transfer energy. It's basically a heat sink. So you're going to have energy transferring from the steel into the concrete. What happens then is the lower flange is going to have hotter temperatures than the upper flange. And because of the thermal expansion, the lower flange expands more than the upper flange. And that's what gives you a smiley face profile for beams. That's one factor. The other factor is applied load bending a weakened steel member. But a lot of people don't recognize that the thermal expansion on the bottom, more expansions are happening there than the top, and that creates a smiley face profile. So here, the bottom member is profiled by these series of thermocouple results. So it's hotter than up high. Now, if you look at 60 minutes, so this is an analysis for 60-minute applied fire rated material. So if you have 60 minutes here, 1100 degrees Fahrenheit is the target for failure, about 538 thereabouts, 550 degrees Celsius. I think this is a little bit more, 600 degrees Celsius, but regardless, it's in that ballpark, and that's the target for this analysis. So at 60 minutes, what you have is you're exceeding that threshold for available resistance to an applied moment load. So you blast past that over time, and then you get above 13 degrees Fahrenheit, where there's just no strength left. Keep in mind, the data logger was limited to 1500 degrees Fahrenheit here when this test was conducted. This would continue rising in elevated temperature. But what's important to note is that when you're designing these facilities, if let's say in this analysis it was 1 hour applied fire resistant material, you were meeting specifications for that bottom flange to avoid failure within an hour using the standard fire. WTC7 was not the standard fire. And so just take away from this discussion, this is how it works. Normally steel in that kind of a configuration would fail down around here. It would fail like in 8 minutes. Very fast failure because of the temperature induced within the standard fire. But because of the thermal resistance of the applied fire resistant material, it's sprayed on insulation, the cementous type insulation, it delays heat transfer longer. It's basically insulation, and that's what gives you your 1 hour rating. So let's talk really quick about restrained versus unrestrained. This is interesting because the definition from ASTM E119 for restrained is that when it's surrounded by a support structure that's capable of resisting substantial thermal expansion. And the reason that's important is the amount of fire resistant material, the thickness, it's going to be different for a restrained member versus an unrestrained member. And that has to do with the thermal expansion. You need more in an unrestrained member to make sure that during thermal expansion, you're not going to lose that fire rated material. World Trade Center 7 had the fire resistant material applied to it based on conditions for restrained members. Now, this is typical, and it's problematic because you'll see that there's issues with that. In the American Institute of Structural Steel, or of Steel Construction, they have specified that, you know, just about any structural application is going to be restrained, and that's not the case. It wasn't the case in WTC 7. And this is what drives it home. If you look for an unrestrained member, a half inch, and this is the W8 by 25, or excuse me, the W8 by 28 beam. That's typical for, ASTM E119 analyses. This is a typical beam you'd use. But take a look at the difference between the unrestrained beam rating with half an inch of fire-rated material applied to it and the restrained. So if you're restrained, you can claim substantially more. There's certain factors involved depending on where the beam is, but you can basically take credit for substantially more fire resistance with half an inch than an unrestrained beam because of that expansion issue. So if I was calling all my beams within a structure restrained, but in reality they weren't restrained, I would lose some of the fire rating protection from that fire resistant material in my structure. And that's actually what happened within this facility. This is actually from One Meridian Plaza in Philadelphia. That was a fire, a lot of similarities between this and WTC 7. It was left to burn, but it was dealt with much prompter within a couple hours. But what you can see is, look at the girder. I mean, just huge deformation of the girders, the smiley face effect. You also see what happened over time, and that's the loss of your fire protective, your fire protection, and that's due to thermal expansion. So it's just a concept that needs to be understood here. Redundancy is an important topic because in WTC 7, let's just examine WTC 1 and WTC 2 really quick. This is actually an image from WTC 1 and 2. And what it shows is multiple arrays of steel. And this worked very well because think about the plane crashing into that structure. You had an airplane come in and it blasted through a substantial portion of the exoskeleton, which did support a substantial portion of the load. But it also blasted through portions of your beams, your girders. And yet the building didn't collapse. And that's a tribute to a very progressive, redundant design. It was very capable of withstanding force. And to be honest with you, the fuel, a lot of people contribute the fuel as the factor for failure. Not quite the case. What you can calculate from the fuel in the fireball that resulted after the plane impact, most of the fuel actually was burned up pretty quickly, in the first, few minutes of the fire. The prolonged exposure actually came from the combustibles within the facility on that structure. So this just demonstrates this principle of redundancy. Let me go back really quick to, basically this chart. So what we're getting at here is, keep in mind with fire protective material, what we're doing is we're prolonging the time before you hit this point here. And keep in mind also that you've just reduced at 538 degrees Celsius, you've reduced your strength by 50%. And also keep in mind, typically when you design a facility, once again, as stated before, you're only about a 25% safety factor. So you're heavily relying on that principle of redundancy. So you're going to exceed localized temperatures in a typical flashover condition. You're going to exceed 538 degrees, particularly if you have damage to your fire-rated material. But in the case of WTC, you had widespread damage because of the length of time that the fire was permitted to travel through that facility. So you had weakened material, and basically it was a combination of expansion and weakened material due to fire rating that resulted in this collapse. But there's one other factor I did want to mention here, and that has to do with this smiley face effect. So as soon as in the vicinity of column 79, once you had the fire transfer its energy into the beams, you had the smiley face form. Well, then what happened? Let's say you have a traveling fire. It's still hot. Don't get me wrong, it's still hot. But as that fire moves to other floors and it leaves this vicinity, what you had now is effectively a shorter beam due to that smiley face and a retraction of the beam or the girder. And that retraction had a bigger delta in terms of thermal expansion because of the new profile than the original expansion of the beam. And that's most likely what caused the girder itself to be removed from the support of the column 79, where this collapse happened. So let's just take a look at a couple things really quick. So back on this, ask yourself, in all sincerity, this was treated as a restrained member for fire rating application. Do you really think this is a restrained member? No, it's not a restrained member. These are not restrained members because there's nothing countering the force associated with this thermal expansion. So what you would have seen happen is if this thermal expansion happened, you would have the column supporting the exoskeleton of the structure pushed out, and likewise this heated up girder here would similarly have pushed in. So you have less fire rating material than necessary. Even though it was approved by code, it was less than necessary because it was treated as a restrained member. In fact, this whole vicinity, because of this unique configuration for the truck drive-through and the electrical substation, it's a unique situation where you don't have restrained members here. So there's no restraining members along these locations. And that's why column 79 most likely failed, because it just was not adequately restrained. So this girder here attached to this column, it likely would have pushed over this girder from its support, and you'd have had some buckling due to eccentricity in the load. So just something to consider. There's nothing nefarious about WTC collapse. This is something that under prolonged exposure you would have expected this to happen. And a lot of people think there's some conspiracy things, some issues were a loud thump heard, an explosion or something. Well, there's a lot of things that could have occurred there. You could have had a localized member fall off of a column, make a huge, a thud, a big sound. There was arguments that flowing metal was seen coming out of this facility. Well, that was clearly an alloying effect between aluminum and copper. It's very common in fires, and a fire of this size would have had substantial aluminum and copper. People have erroneously assumed, because of the 1960-degree temperature melting point of copper, that you wouldn't melt in a fire that was like 1200 degrees Fahrenheit. That's not quite true, because you're going to have molten aluminum at 1100 degrees Fahrenheit, and it's a principle. It's called a eutectic alloy. And what happens is you can have alloying elements, aluminum and copper alloy, at cold temperatures, at the temperature of aluminum's melting point. So if a molten aluminum falls on copper, it will alloy even though it's below copper's melting point. And the result is a lower temperature or melting point than pure aluminum or pure copper. And alloy, I mean, take tin lead solder, or take the eutectic metal in the fire, the sprinkler heads. There's eutectic metal in there that has a low melting point. I mean, 165 degree Fahrenheit heads, for instance. So the alloy itself has a lower melting point. So what would happen is, by molten aluminum, and you're going to have a significant amount of molten aluminum in a facility. So you're going to see that flowing. You're going to see the alloy between aluminum and copper flowing. And if there's zinc, lead, you're going to have a lot of flowing through this old facility. So there's nothing nefarious about that. This was very reasonable. That some people have claimed that there was thermite residue, like it was painted on. Well, there's other telltale signs that could have produced that chemical footprint. So the assumption that there was something nefarious with the destruction of this facility when it burned for 7 hours, when the material was only rated for 2 hours, when you had this funky, unrestrained design because of the electrical substation and the truck drive-through. All the models point to a normal collapse in those situations in the absence of both automatic suppression and manual suppression, manual firefighters. So it's very predictable. This isn't something weird. So let's just take a look at our conclusion. Thermal expansion and cooling, that was the mechanism for failure. Um, the structural spray applied fire resistant material was for restrained, not unrestrained beams, resulting in faster failure for those beams. The structure was designed for life safety. It was not designed to avoid collapse. And it worked very well for life safety, but it does raise another question. If you're designing a facility exclusively for life safety, well, how does that affect other people in a major metropolitan, big area like New York City? If you're going to have structural collapse, it's going to impact operations for other facilities. It's going to have a huge impact. So life safety itself as the principle for design may not be sufficient. There's other very impressive designs. The Cook County Administration Building in Chicago, for instance, the fire that occurred there, it killed a few people. Um, the structure itself handled the fire extremely well. It was, the stories where it occurred was down for just a short amount of time, fixed, flashover conditions. What I'm getting at is you can build structures that can resist collapse, but the focus for the most part is on avoiding injuries, avoiding fatalities, and it may not be an appropriate design. A redundancy needs to be applied, but it's only designed. Redundancy is only for like a flashover situation in a small area of a building. It's not designed for the kind of very unique situation that WTC-7 experienced, where you had a traveling fire for 7 hours. So I guess the real conclusion is a lot of people out there that oftentimes are fairly ignorant. These individuals aren't engineers or scientists. They're coming to conclusions on WTC-7 that it had to be some conspiracy, and maybe something was there, but the evidence just doesn't support that. So it's not. I think the conspiracy. I hate to use the term conspiracy theories because obviously there's a lot of conspiracy theories that are conspiracy facts. When there's money involved, you're going to see some subversion of evidence. But in this case, it's really not associated with an unnatural event. This is something that is predictable. So, in any event, with the danger of promoting those conspiracy theories, those false theories, really unprovably false theories, is that it creates mistrust in the government, mistrust from our enemies and allies, and it results in violence. So promoting those type of theories or hypotheses that are unfounded, it's dangerous. So make sure there's really good scientific evidence for the support of those kind of accusations. In any event, so thank you for your time. And just to give you my background, I guess I should have done this at the intro. So I do have some background in this field. So I'm registered in mechanical engineering, registered in fire protection engineering. I have a couple, two different masters of science degrees in different engineering fields. Fire protection engineering and mechanical engineering is applied in manufacturing operations. And I'm a certified building official. I've wore lots of hats. I've also, for several years, been the authority having jurisdiction over a major nuclear research and waste handling facility that's funded by the Department of Energy and Department of Defense. So, my perspective, I do have some experience in this, a reasonable perspective. So, I'm not blowing smoke. So, hey, thank you for your time, and I hope you enjoyed this video, and have a good day.